I'm very pleased to introduce today Dr. Kevin Hand from JPL, the Jet Propulsion Lab. He earned his degrees from Stanford and Dartmouth. He's a planetary scientist at JPL, where he directs the Ocean Worlds Lab. His research focuses on the origin and evolution and distribution of life in the solar system, with an emphasis on Jupiter's moon, Europa. His work involves both theoretical and laboratory research on the physics and chemistry of icy moons in the outer solar system, and he served as in a variety of positions, including on several of the current and recent mission concepts. Rather than read that in detail, since we're running a couple minutes late, I'm going to yield the floor to Kevin Hand. I guess we should go for 40 minutes or so and then take some questions. And if I'm not online at the end, then Bill or Sean will moderate the questions.
Absolutely.
Kevin, the floor is yours. Thank you.
Excellent. Thanks, David. And I'm going to go at like 1.5 speed for some of the opening stuff. Some of it's review, but framed in perhaps a different context than you've seen before. And it's great to connect with this crew. David and I have been working together for a number of years. I'll touch on some of that, but pleasure to be with you all virtually. So to begin with, one of the most exciting and arguably one of the most profound discoveries of the past 60 some odd years of solar system exploration is that we now know, or at least have good reason to predict, that oceans exist beyond Earth. Oceans exist as a planetary phenomenon, perhaps as common as atmospheres and rock cycles, etc. And so it's through missions like Pioneer, Voyager, Galileo, Cassini, and more recently New Horizons and Juno that we have good reason to predict that at least 6 moons, and potentially many more moons of the outer solar system, harbor liquid water oceans beneath their icy shells. And these ice-covered ocean worlds of the outer solar system are really changing our understanding of what it means for a world to be habitable. In the early days of astronomy and planetary science, our conception of habitability was constrained by our own thinking about what it meant for Earth to be habitable. And we had this kind of Goldilocks scenario. If you were too close to the sun, you were too hot and lost any water that you once had. That's sort of the short version of the story for Venus. If you were too far away, you didn't get enough energy from your parent star, and water that may have been on your surface eventually froze out. And that's sort of the short story for Mars. It's much more complicated than that. But then if you're at just the right star planet distance, as the case is for Earth, you could maintain and sustain liquid water on the surface. You could harbor an ocean that could then give rise to life. But as we know by studying and discovery of these alien oceans beyond Earth, this is kind of an old Goldilocks. There's a new Goldilocks in town, and it's one wherein the energy to sustain and maintain liquid water oceans comes not from the energy of your parent star, but rather from the tidal energy dissipation that occurs as these moons orbit their giant planet primaries. And there's no better example of the extraordinary amount of energy dissipation that occurs in some of these moons than Jupiter's closest large moon, Io. Io does not have an ocean, but Io is the most volcanically active body in our solar system, more volcanically active than the Earth. Shown here is Io with a volcano erupting near the North Pole. And in this sort of new Goldilocks framework, Io is kind of like Venus. It's too hot, it's got too much energy. It lost any water that it may have once had. And Callisto, the furthest out of Jupiter's 4 large moons, Callisto may be sort of analogous to Mars. Callisto in the tidal energy Goldilocks zone, the new framework for habitability. Callisto, we don't think has much in the way of tidal energy dissipation, but it may have enough radiogenic decay from heavy elements so as to sustain sort of a slushy ocean beneath a thick ice shell. But it's really Europa and Ganymede, and Europa in particular, that provides the type example for this new Goldilocks. Europa has been in existence for much of the history of the solar system. It's got just the right amount of tidal energy so as to sustain what we think is probably a 100-kilometer deep global ocean. And above that ocean is an ice shell that is comparatively thin. In the case of Europa, we think the ice shell is of order 10 kilometers thick. It might be a few kilometers thick. It might be 20 kilometers thick, but it's in that range of about 10 kilometers. And it could be highly heterogeneous. It might be thin in some areas, thick in others. Ganymede and Callisto, by comparison, probably have ice shells that are closer to 100 kilometers in thickness. So Europa, when we look at Europa's surface, we think that the ice shell is thin enough and recycled rapidly enough on geologic timescales so as to provide a window into the ocean below. And this new Goldilocks, the fact that these oceans exist beyond Earth, present an incredibly compelling target for us when it comes to the search for life beyond Earth. If we learned anything from life on Earth, it's that where you find the water, you almost always find life. From life in extreme environments, as shown here, to life of extreme lifestyles. All life on Earth requires liquid water. I heard a couple of chuckles out there, which means that thankfully I've got an audience that at least remembers the Rolling Stones. Sometimes I show this slide to younger crowds, and I feel like I need to switch it out for a pop star. But Mick and Keith here, I like to show them for another reason, and that is for all of the diversity of life on Earth. We're really all the same, from the most extreme of microbe in a hydrothermal vent to the most extreme of rock star. We are all connected by the same genetic tree of life. That tree is dominated by microbes, bacteria, archaea, and even the single-celled eukaryotes. This is our tree of life. Mick and Keith and all of us would be sort of down at a little twig in the bottom right there. And part of what fascinates me about the search for life within these alien oceans is that these are places where we can go and potentially search for a second or third or fourth independent origin of life, independent trees of life that may be based on different biochemistries from what we have here on Earth. Is there some other game in town beyond the DNA, RNA, ATP framework that builds all life on Earth? That's an important distinction when we think about our solar system exploration. I am a scientist on the Perseverance rover. I love the search for life on Mars. We're going to be returning some rock samples from Mars in the next decade. And that's incredibly important and very exciting. But on Mars, we're looking for molecular organic remnants from life that existed 3.5 billion years ago. In those ancient rocks, we are not going to find molecules like DNA or RNA or whatever some other organism might use. And that's unfortunate because we're going to have a very tricky time connecting any putative discovery of biosignatures in ancient rocks on Mars to the past history of life on Earth and distinguishing whether or not that evidence of life on Mars was in fact connected to life on Earth at some point in the past. These alien oceans of the outer solar system, first and foremost, they're hard to cross-pollinate. Earth and Mars have been trading material for billions of years. And so life on Earth could have seeded life on Mars or vice versa. Europa, Ganymede, Callisto, Titan, Triton, and Enceladus, these moons are too far away to really provide consistent, viable pathways for cross-pollination. It's not impossible, but it is quite hard. And then, and so were we to discover life on these worlds, I think we could reasonably conclude that it is independent from life on Earth. And then coupled with that, were we to find evidence of life on the surface ice of these worlds, we would have good reason to conclude that that life connects to extant life in the ocean below. Again, the ice shells provide a modern window into whatever is happening in that ocean below. The ice on the surface of these moons is geologically young. So whatever we find on the surface is probably indicative of whatever's happening in the recent past in the ocean. And the discovery of extant life could then give us the opportunity to understand its biochemistry, its origin, and its evolution. Now, the tidal energy Goldilocks scenario, where that provides a new mechanism for maintaining liquid water oceans, that's just one kind of Goldilocks framework that I like to map onto the requirements for habitability. If we think about the keystones for life, we're really talking about life as we know it, needing liquid water, the elements to build life, and some energy, be it photolytic or chemical, through which life can operate its metabolism for growth and reproduction. I won't go into detail on these right now, but I'll just kind of go through a few key things to provide some a little bit of context for the framework. With regard to tidal energy, we can look at the Earth. Earth's average seafloor dissipation is somewhere between 60 and 80 milliwatts per square meter. On Io, which as I mentioned is the most volcanically active body in our solar system, we're looking at 2,500 milliwatts per square meter. That is extraordinary. Io is a phenomenal world to study in the context of volcanism and mantle evolution, and there's some electromagnetic induction evidence for a magma ocean beneath the crust of Io. It's really quite a fascinating world in its own right. But when it comes to habitability, Io is not a place to look for life. Europa, when you look at the tidal dissipation, we don't have very good constraints on what exactly is happening in Europa's ice shell and in its mantle, but the models predict that Europa falls somewhere between a 10 milliwatt low end and an 800 milliwatt upper end per square meter of energy flux. That, as you can see, could be in the range of Earth or an order of magnitude above Earth's average seafloor flux. I will say that the bottom end there, the 10 milliwatts per square meter, that's basically the radiogenic flux if you just took out all tidal energy dissipation. And so that's a pretty extreme low end for Europa. We know that it has to be dissipating some degree of tidal energy, but in the published literature, there's some pretty conservative models. Enceladus is a weird case. I'll get a little bit into this. It's got about 16 gigawatts emanating from its south polar terrain. Globally averaged, you can do the math, and that ends up being roughly 200 milliwatts per square meter. But Enceladus definitely has this weird hemispherical dichotomy that really points to the southern hemisphere as being the source of its energy flux. How exactly is this maintained? Is tidal energy just a transient phenomenon? Don't orbits change and kind of evolve out of this energetic sequence? Well, in the Jovian system, Mother Nature has played a fun trick with the three innermost large moons, Io, Europa, and Ganymede. It's a beautiful sort of swing set resonance called the Laplace resonance, where normally moons would lose some of the dance between the moons and the primary planet, would result in a loss or transfer of angular momentum. And eventually you would not have any eccentricity to your orbit, and you would not have any tidal tugging and squeezing that would create internal heat and the heat needed to sustain oceans. But in the Jovian system, this Laplace resonance results in Io and Europa and Ganymede, each tugging on each other ever so gently so as to maintain this resonance where they have a forced eccentricity coming from the radial tide component. And this eccentricity has maintained heating in these worlds perhaps longer than would otherwise have been possible if this Jovian large moon setup was not curiously set up for this Laplace resonance to take place. As I'll describe in a minute, the mid-sized moons of Saturn create a bit of a transition of resonances, and so nothing is sustained through time nearly as persistently as what we see with Io, Europa, and Ganymede in the Jovian system. Callisto, marked with a big X there, is not part of this resonance, but perhaps someday this will become a four-body resonance. So in the Saturnian system, there's a variety of resonances through time. This paper by Meyer and Wisdom from a number of years ago shows in kind of a primordial version of, if you take all of the mid-sized moons as having been around for the history of the solar system, here is what some of those resonances would have looked like through time. And in the modern, Enceladus and Dione are currently in a 2-to-1 resonance. Now, with Enceladus, as much as I love Enceladus, a lot of questions remain as to its tidal energy dissipation and where it is getting all of this energy. And a lot of this comes back to the uncertainty about the tidal quality factor for Saturn. This quality factor we refer to as Q. Q, as I write at the bottom there, is this ratio between the maximum energy stored in tidal distortion. So you can think of an atmosphere, an ice shell kind of raised out of equilibrium. And then the energy that is available for dissipation through friction as that atmosphere relaxes or as that ice shell or silicate mantle is relaxed. And in the case of Saturn, initially the thinking was that Saturn had quite a large Q of 18,000. And in that case, these mid-sized moons like Enceladus and Tethys and Mimas, etc., could be primordial. They could be as old as the solar system. But the irony here is that if you accept that higher Q value and can then explain the existence of these moons as being primordial, you then have a really hard time explaining heating at Enceladus. Flip that around, some more recent work has said, well, one way to solve the problem of heating at Enceladus is by lowering the Q of Saturn. This lower Q in the range of about 1700 is consistent with the archival data of tidal recession. In other words, the decades and in some cases centuries of monitoring of the moons of Saturn and looking at recession through time. So that archival data plus the Cassini observations support this, this migration of the moons, and that lower Q factor can explain the tidal heating in Enceladus. But the caveat here is that it requires these mid-sized moons to then be astronomically or geologically young, somewhere in the range of 100 million years. This second Q value also helps explain the rings of Saturn, shown, of course, right there. Rings around any planet are hard to explain. Rings are indicative of an instability. Something happened over billions of years. Rings, the dust, the particles that make up rings either get gravitationally sucked into their planet or they get dissipated out, depending on where they fall with respect to the Roche lobe, etc. So the rings of Saturn are kind of a fingerprint of some tumultuous activity at some point in the past, and it's actually hard to explain the rings as being billions of years old. So this lower Q value is actually quite helpful in explaining a number of observations of the Saturnian system, but it then means that Enceladus might be quite young. And if Enceladus is quite young, would life had enough time to originate, and would Enceladus be stable enough for sustained habitability? I don't know, but this is just something where, at least when I consider Europa and Enceladus and what it takes for life to arise and for life to take hold, I do like the idea of having an ocean that's been around for billions of years and potentially more stable than an ocean that's younger and perhaps a little bit more chaotic. And so from a habitability standpoint, I typically often rank Europa a bit over Enceladus for this reason, this uncertainty that we have about the age of Enceladus and how long its ocean has been around and what kind of energy is occurring within that ocean. Enceladus is extremely exciting, but there is too much of a good thing. It may be that Enceladus is more like an Alka-Seltzer tablet just fizzing away with energy, and too much energy may actually be overwhelming to the origin of life and to habitability. But we just don't know. We got to get out there and we got to explore these places. Okay, that's a little bit on the Goldilocks for tides and oceans. There's also a Goldilocks when we think about elements and what it takes to build life. And shown here is a periodic table highlighting some of the key lighter elements and heavier elements that life needs. And curiously, when we think about the Earth, our home planet, which we think of as being ideally suited for life, when you dig a little deeper on our home planet, it actually turns out that Earth is not a good place for life. If you were just looking at our solar system from afar, if you were a distant civilization looking at our solar system in the early years, you would probably neglect the inner planets as being too rocky, too dry, and not a nice place for life. Of course, as we know, we think that Earth got a lot of its water from subsequent dehydration of the mantle and delivery of ices and water from comets and asteroids. And so Earth had this nice delivery of volatiles post-formation. Meanwhile, the outer solar system is where a lot of the light elements that life needs, the carbon, hydrogen, oxygen, nitrogen, and phosphorus, and sulfur, these are where the ices condense out. You're in the Jovian system or Saturnian system, and you condense out ices of methane and sulfide and ammonia and SO2 and so on and so forth. And so in this kind of simplified version of the Frey and Schmidt phase diagram here, you can see that the worlds like Europa and Enceladus are rich with these lighter elements in the forms of condensed phase volatiles that form the ices that we know and love on these worlds. So light elements, the outer solar system is rich in those. What about the heavier elements? Well, here we can do kind of a quick classification based on density and how these moons rank. If you're too low in density, then sure, you might have some of those light elements that life needs, but you might not have a good mixture of water with, say, iron and nickel and magnesium and these other things that life as we know it requires. So you want to be relatively dense so as to supply some mechanism for water to interact with those elements, providing a catalytic surface on which life can originate, and then enzymes can form and so on and so forth. So when you look at a diagram like this, if you get too high up, you might have too much rock and too little ice, such as the case for Io and the moon. Europa, interestingly, resides kind of up in this classification of rocky satellites. It comes in at about 3,000 kilograms per cubic meter. If you're too far down, you might have too much ice, but too little rock. Enceladus may fall into this case, Pluto perhaps, etc. I wouldn't say that there's a specific dividing line here. It's just kind of an interesting framework through which to think about access to the heavy elements. And then the last kind of grouping here, these are worlds where if you get too big, if your radius is too large, and your mass is too great, now you end up having not just a surface of ice over your ocean, but you also have high enough pressures at ocean depth such that you have an icy seafloor. And while you may have rocky silicates, some of those heavy elements in your interior, this icy seafloor has perhaps cut off your liquid water region from interacting with those heavier elements. So that's both the light and heavy elements. With respect to carbon, as I mentioned, whether it's the volatiles or the formation of the giant planets themselves, the outer solar system is a place that is abundant with carbon, with nitrogen, with phosphorus, sulfur. And in the Jovian system, we have seen carbon and nitrogen on Callisto, some tentative evidence of it on Ganymede, and we've seen carbon in carbon dioxide on Europa. We have not seen organic carbon on Europa. And that may be, that evidence, that absence of evidence may be perhaps more indicative of challenges that we had with the Galileo spacecraft than it's not like we got a thorough chance to really examine Europa's surface. The Galileo spacecraft had troubles with the high gain antenna. And as a result, upon approach to Europa, we were challenged with radiation noise in the detector, and then limitations on how much data could be collected and transmitted. But Europa's nearest neighbors do actually have carbon and nitrogen. All right, let's dive briefly into Enceladus and then Europa, and we'll get into some lab stuff. I think many of you are familiar with Enceladus. It's a curious small moon, just 500 kilometers or 300 miles in diameter. It's about the distance from Chicago to Cleveland. And of course, in that southern terrain, we saw these tiger stripes. And upon closer inspection, with beautiful geometric arrangements like this, as made possible by the engineers, the Cassini spacecraft was able to approach the south polar terrain at just the right angle with respect to the sun, so as to see this beautiful reflection of the sunlight off of these jets emanating from the plumes gushing out of the fractures. And along with collecting that imagery, the Cassini spacecraft also had on board 2 mass spectrometers, which allowed a tasting of the plume material. The first few passes resulted in data primarily from the ion and neutrals mass spectrometer shown at upper left. And that data revealed methane along with the water vapor, some small chain simple organics, possibly some fractionation of more complex organics, and then carbon dioxide. And as exciting as this data was, many of us in the planetary science community said, well, let's not jump to the conclusion that these plumes are connected to an ocean below, because in fact, when you look at a mass spectrum like that in the upper left, we actually have seen very similar compositions in things that have definitively no connection to an ocean, objects such as comets. Comets have jets erupting out of them, and they are very organic rich. So there was a period of time back in kind of the late 2000s where many folks, myself amongst them, were quite cautious about how to interpret the early mass spectrometer data. But then with subsequent flybys, the Cosmic Dust Analyzer, the CDA on Cassini, also got to taste those plumes and the E-rings, the E-ring, which is sourced by the plumes. And in that data, we then started to see not just water and organics, but also salts. And salts, for any geochemist, for any planetary scientist, salts are highly indicative of water-rock interaction. Comets are not rich in salts. You need to have some liquid water leaching through silicates to pull out those ions. So once we started to see that data for salts coming out of the plumes of Enceladus and entrained in the E-rings, that's when folks like myself and others really started to believe in this hypothesis of the ocean below. And then subsequent to that, the CDA discovered silica, SiO2, and also with the ion neutral mass spectrometer, an excess of molecular hydrogen was discovered. Both of which points not only to an ocean, but also to an ocean that is underlain by a rocky seafloor, and perhaps even a seafloor that is undergoing active serpentinization, a geochemical process that occurs at off-axis hydrothermal vent sites, such as Lost City in the Atlantic Ocean. And serpentinization is a very exciting geochemical process from the standpoint of the origin of life, and also from the standpoint of chemosynthetic pathways that life on Earth uses, and which could serve as a running through here. So you got my screen now, right, David?
Yes, good.
Excellent. Okay, so here's what Enceladus looks like. You all know and love it. Let's move on to Europa. Europa is 3,000 kilometers in diameter, much larger than Enceladus. It's about the size of our moon shown here with respect to the Earth and Jupiter. Of course, Jupiter is some 318 times as massive as the Earth. And so you can imagine the tidal tug and pull that Europa experiences. I like to explain the discovery of Europa's ocean in 3 easy pieces. Yes, that is a riff off of Feynman's 6 easy pieces. It's beautiful physics. I love it. I'm not going to go through it today. I forgot to mention at the beginning of the hour that I wrote a book called Alien Oceans, in which you can find a chapter on each of these 3 easy pieces. So if you want more detail on that, please read the book. I want to focus in on a bit of a mystery with respect to Europa's surface chemistry, and that is that unlike Enceladus, which is quite white and homogeneous in color and spectroscopy, the surface of Europa has this bizarre patina of red, yellow, sort of brownish discoloration. And that discoloration is often associated with these fractures and freckles and various things geologically on Europa that we hypothesize connect to liquid water below. And so there's long been a debate about, is this yellow, red, brownish material oceanic? Is it perhaps a salt from the ocean below? And in the early days of Galileo results, there was one camp that argued that the NIMS data, the near-infrared mapping spectrometer data shown there in bold on the upper part of this set of spectra, the NIMS data is well fit by magnesium sulfate brines or sodium sulfate brines. And you can see, yeah, okay, it kind of matches, but what's most diagnostic there are the absorptions at 1.5 and 2 microns. And that's really just diagnostic of water ice. The more nuanced absorptions, say at 1.6 and 7, et cetera, those are harder to see in the NIMS data. And yet that really is what helps you differentiate a frozen ice from frozen ice that's got salt in it. And Bob Carlson, who was the PI of NIMS and who sadly just passed away 2 weeks ago, Bob was the fiercest critic of this salty interpretation because, as you can imagine, the salt hypothesis for the NIMS data was the most extraordinary hypothesis. It implicates a salty ocean below, whereas there's actually a more simple hypothesis, and that is that the NIMS data is best explained by sulfuric acid hydrate. Now, sulfuric acid hydrate may not seem like a simple hypothesis to you, but as I'll explain, there's an easy character to implicate in the sulfuric acid pathway. So on Europa, there is this fingerprint of this hydrated sulfate of some form, and that fingerprint is primarily on the trailing hemisphere of Europa. Europa always shows the same face to Jupiter, and therefore it's got a leading hemisphere, the hemisphere that's kind of forward facing in its orbital path, and a trailing hemisphere, kind of the rear end of Europa as it runs around Jupiter. And that trailing hemisphere of Europa is constantly bombarded by sulfur ions from that volcanism that occurs on Io. So Io spews out sulfur, and then ions of sulfur impart the trailing hemisphere of Europa. And that radiolytic processing of the sulfur then quite logically leads to the creation of sulfuric acid hydrate. So exogenous sulfur comes in, bombards the H2O, the water that's there, and you radiolytically yield H2SO4 hydrate. And so Bob, his work in the early 2000s on this, I think quite strongly show that much of what we see on the trailing hemisphere of Europa and much of what carries that sulfate signature is in fact H2SO4 that is predominantly exogenous sulfur. So it does not implicate salts from an ocean below. The endogenous MgSO4, that second bullet, I don't think we can rule it out, and there is definitely nice work on that. But personally, spectroscopically, I don't think that the NIMS data requires the hydrate. The third bullet there, endogenous magnesium, my colleague Mike Brown and I, we got some new data from the Keck telescope, and we think we may have found a new spectral feature that implicates magnesium sulfate hydrate. I won't go into that. Rather, I want to go to the fourth bullet, was implicating something else altogether. And this brings us to the lab. And I want to give note to our lab team here, Dan Beresford, who I think many of you know, Jeff Foster, Ben First, Jay Kosberg, Lavina Bachman, and then a suite of just brilliant students that have worked primarily on the modeling work that I'll get into a little bit later, or at least I'll get into the experiment side of this. But Zoel and Antonio and Andy and Anthony have all just done fantastic work in partnership with our lab experiments here. And that's been a real nice partnership between JPL and UT Austin, spearheaded by David. So in the lab, I've got these chambers where I can replicate Europa at the micron scale and at the meter scale. And the experiments that I want to highlight now utilize what I call our MINOS chamber, Europa in a can. We get down to Europa temperatures, Europa pressures, and then we turn on the electron gun and irradiate the material in the same way that material on the surface of Europa is irradiated by energetic electrons and ions that are trapped in the Jovian magnetosphere and bombard the surface. And here I was curious about sodium chloride. If Europa has a long-lived ocean, then it's reasonable to expect that sodium chloride would in fact be the dominant salt, the same way that it is here on Earth. And I won't get into the geochemistry of why sodium chloride has a longer residence time than, say, magnesium sulfate. But suffice to say, sodium chloride is the dominant salt in our ocean for geochemical reasons, and therefore, if you've got a long-lived ocean elsewhere, you might expect sodium chloride to also be the dominant salt. The problem is that spectroscopically, sodium chloride is flat. There are very few features. It appears optically white to our eyes, and spectroscopically from the visible on through the mid-infrared, there's essentially no features you can pull out. However, after irradiation, and here's sodium chloride salts in evaporitic brine within the MINOS chamber. After irradiation, alkali halides like sodium chloride turn a variety of different colors. And in the case of sodium chloride, it turns this beautiful yellow or brown color, depending on exactly what temperature and what form you have the salt in. And what's happening here is that there are anion vacancies within alkali halides that then trap electrons. Here again, it's beautiful physics. In the early days of studying this phenomenon, the trapped electron was used as an analog to the harmonic oscillator. A lot of just nice quantum mechanics work that was done in the early to mid part of the last century on this. Fast forward to 2015, and we're applying a lot of that to our experiments looking at salts on the ices of these distant alien oceans. Now, when I first pulled those samples out of the chamber, immediately my eye was drawn to the comparisons with this discoloration we see on the surface of Europa. And I went to the data available, but we really did not have good spectroscopic data through which we could match the color center absorptions of sodium chloride, the positions of which are at 460 nanometers and 723 nanometers. So in this plot at left, you can see the brine and salt grains with water. And those specific absorption centers both provide the discoloration and also provide really diagnostic spectral features that you can go after to detect the presence of these irradiated salts. The colored bars there are from the solid state imager on the Galileo mission, but as you can see, the band passes of those filters did not really match up well with the absorptions. That led to Samantha Trumbo, a grad student down at Caltech, working with myself and Mike Brown to write a proposal to get time on the Hubble Space Telescope. And what was jaw-dropping about those spectra that we got from Hubble, which you can see in the upper right, the black spectra there, is that with Hubble, we're able to see this very distinct absorption around 450 nanometers that matched quite beautifully the red line there, which is my lab data, which is indicating that F center, that color center absorption, those trapped electrons in the sodium chloride. And we found that on the surface of Europa, geographically tied to this region near the leading hemisphere that has this yellowish color that even to the eye matches quite nicely with what we see there on the surface. So a beautiful experiment connecting the lab experiments to this question about the composition of Europa's surface, to then the follow-up with the Hubble data. I want to jump to the morphology of Europa, and here's where we'll get into a few of those experiments related to the modeling that many of the students at UT Austin are doing. This is a mosaic of the highest resolution images we have of Europa's surface. This is a grayscale image, and we're at about 6 meters per pixel here. The cliffs that you're seeing are perhaps 100, 200, 300 feet in height. The gray, black material that you see could well be yellow or brown. It could have lots of salts in it, could have organics in it, it could have jellyfish in it. We just don't know. And along with looking at the radiolytic chemistry and understanding the spectroscopy of worlds like Europa and Enceladus and what's happening on their surface and in their icy surfaces, our team is also looking at the morphology, the evolution of ices on these airless bodies. And that's led us to explore some regions on Earth that have some interesting analogs to the sublimation-driven environments that we see on worlds like Europa. Shown here is the northern ice field of Kilimanjaro. I was up there doing some work back in the late 2000s. An absolutely stunning environment, sadly disappearing quite rapidly. I was collecting some samples in the different strata of the ice fields. And I was also examining the top surface, which, given the high altitude and the equatorial exposure to the sun, leads to penitente formation on the tops of these ice fields. And penitentes have long been studied on Earth. Here you can see a card showing the height of these penitentes. They're called penitentes because they are penitent, they are praying to the sun. And in this case, you can see that they're all pointing quite direct up. That's because we're near the equator and the sun is passing overhead. If you go kind of at higher, more northerly or southerly latitudes, you can see more of an angle in the penitentes. But there had been some work arguing that Europa's surface, and for that matter, Enceladus' surface, is going to be dominated by penitentes that are 15 meters in height, or just, these gigantic castles of penitentes covering the surface. And there are reasons empirically to think that is not the case, but from a physics standpoint, I had long been looking at this possibility and had resisted the temptation to publish on this kind of extraordinary claim of and somewhat exciting claim that, you know, Europa might be a field of penitentes. And the reason I was hesitant to do that is because Europa is not the Earth. Europa has no atmosphere. There is no vapor diffusion layer on Europa. And on Earth, this vapor diffusion layer, this atmosphere that we have, gives rise to the relative humidity above the ice in, say, the northern ice fields of Kilimanjaro. And that is an important part of the temperature dynamics, which then gives rise to the heat within the penitente troughs. On Europa, we're talking about molecules having mean free paths of hundreds to perhaps even thousands of meters, and conditions for penitentes, the physics that is well described for penitente formation on Earth, requires at least some fluid layer covered with irradiance and self-illumination. So we published a rebuttal to some of that high-profile work that came out, I think, in 2018, and we just looked at the theory side of what happens as you remove that boundary layer using the physics for penitentes as we know it. And what ends up happening is that as you get rid of your atmosphere, as you get rid of the fluid regime, you go to this limiting case of smaller and smaller penitentes, and eventually you have uniform runaway sublimation. Coupled with that, we decided to do some experiments. And here's the arc chamber at JPL. And I'll just very quickly go through this. There's Dan in the upper right. This is a chamber where we can grow ices and then have a solar irradiance LED network raster over the ice to simulate ice evolution through time. Here's that ice freezing. This is just kind of a beautiful video of the initial process of getting the ice to form. And then once the ice forms, this is clean ice. We just do a diurnal, this is 3.55 days that it's taking the light bar to raster over. And that 3.55 days corresponds to the European day-night cycle. And we just let it go for months. You can see the temperature there. Gradually, we increase the temperature just because we wanted to do this on a human timescale, not on a geologic timescale. So I'm just going to skip ahead. You'll see we go up to 160 to kind of increase the rate of migration of water molecules, eventually up to 170 K. And what we saw with the pure ice, flat ice morphology is that we could not form penitentes. Rather, we ended up forming some interesting botryoidal, some rounded-like features in the coldest regions of the chamber. And these cold trap features, we're currently working on writing up these results. They had nothing to do with the penitente physics. They were not a response to the self-illumination and solar irradiance components that are critical for penitentes. It all had to do with the fact that that area where you see this kind of marshmallow structure is right over the cryostat that's providing just a slightly colder temperature than the perimeter walls of the chamber. And that's where students like Zoel Wong and Andy Su have done some really nice modeling work on the sensitivity of our experiments to temperature differentials across the chamber. We looked at snow. We created some snow and dumped that into the chamber. And here again, we found that even if you seed the chamber with strange morphologies, the energetics of sublimation lead to erosion and eventual flattening of the surface. So no migration to penitente-like features. And then more recently, we've actually seeded the chamber with a cake that has this corrugations analogous to penitentes. Here's that cake in the chamber, looking from the side. Here it is head on. And as this runs, you'll see a gradual erosion of the peaks while the trough stays at the same level. And this in part is due to the fact that the energetics of water molecules popping off of the icy surface promote loss of water from the more exposed peak regions, whereas the troughs, even though they appear to benefit from enhanced heating from self-illumination, the troughs don't actually get hot enough to outpace the erosion of the peaks. So even with seeding an airless body, an experiment that's simulating an airless body, even with seeding the chamber with penitentes, we still cannot get a feedback loop that promotes penitente growth. Now, there's still questions to ask and things that we're examining, but at this point in time, our experiments and the modeling work that folks like Anthony and now Andy and Antonio are pursuing that couple with these experiments, they really show an interesting migration of sublimation features away from penitentes and towards flatter surfaces. We're looking at some variations on that, but the story at this point is that sublimation leads to flattening. Okay, I realize we're coming up on the hour here, so I'll just finish with what's next. We've got the Europa Clipper mission, hopefully being launched in October of 24, just about 2 years from now. The ESA mission, the Jupiter Icy Moons Explorer, is hopefully launching around the same time. We've also got the Titan Dragonfly mission. I'm a co-I both on Clipper and on Dragonfly. I didn't talk about Titan today, but that's a fantastic mission that's going to explore the equatorial dune region of Titan. And then for much of the past nearly 2 decades, I've been helping spearhead not only Europa Clipper, but also trying to get a lander to Europa's surface. With the release of the most recent decadal survey, this mission is now essentially being mothballed or canceled and replaced by a Uranus orbiter, and off in the future, some Enceladus orbiter. So very sad, but we actually have done a lot of work on this mission. Shown here is a prototype with a fully autonomous robotic arm that we deployed on a glacier up in Alaska back in July and August. And so I'll finish with this pan over that shows you this exciting Europa analog, this glacier, the Matanuska Glacier in Alaska, with all its crevasses and chaotic looking features. Our team, we hiked in and out. I was up there for the first week of deployment. The engineering team was up there for the better part of 3 weeks. And within hours of having our lander and gear helicoptered out, the lander was up and running with a robotic arm, doing sampling of the glacier ice. The position that you see it in here was the first locale that we had it deployed. We then sent it over into one of the crevasses and had it sample some of the more difficult terrain. But what our Europa Lander mission concept really pushed on, along with some of the landing technologies, was also autonomous sampling. On Mars, when we go to get a sample, there's a lot of ground in the loop work with the engineering team. So we collect images to create a DEM of the surface. The engineers then look at that DEM for a day or two, and then the science team kicks it back and forth with the engineers on what's a safe site and where can we sample. This robotic arm with the cameras on board and some of the other sensors on board could do that DEM generation and analysis of a safe sampling site all by itself. This is push button autonomy. And that's key, because when you're out at Europa or Enceladus or any of these distant worlds, you don't have the merit of a relatively quick cadence with that world. On Mars, we've got that 7 minutes of terror during landing, but in terms of operations, that also means that we've got a relatively nice communication sequence, and we've got a lot of assets in orbit around Mars that give us a lot of data back from that planet. You land on Europa, you land on Enceladus or elsewhere, you're going to want a robot that's got some built-in autonomy that can do work well you cannot have ground in the loop. And so this field demo just did a fantastic job of showing how mature our Europa lander mission concept is. We've put about $300 million into the various subsystems of this, and it's quite sad that it's now essentially canceled. So I'll close with a thank you. Sorry for running a bit over time and with the Zoom complications, but as I mentioned, I tried to speak quickly to cram it all in. Thanks to our Ocean Worlds Lab team, our brilliant interns at UT Austin, and the Europa Lander Mission Concept team. Thanks. I'm happy to stick around.
So we are over time, so I know a lot of people already had to drop off. Maybe we can just take a couple of questions. Yeah, and then anybody have a question on the Zoom world or in the room? If you're on Zoom, just go ahead and then unmute and ask your question.
I had a question. Hi there, this is Marquez. I'm from UT. You mentioned the discussion of the tidal quality factor for Saturn and how this may or may not explain Enceladus sort of heat production. Are there any similar arguments for Jupiter, or is that just astronomically a different ballgame?
I'm sorry, say that again.
So for Enceladus, I believe you mentioned that people are thinking of revising the tidal quality factor Q for Saturn.
Yeah.
And is there a similar argument that applies to Jupiter, or is that just different, the orbital mechanics?
Yeah, it's a good question, and one to which I don't really have a good answer. I'm not embedded enough in the latest that's coming out of the Juno mission. And so the Q factor is a topic of much debate in the community. The Juno mission has been orbiting Jupiter for the past, half a dozen years at this point. And a lot of the goal of that mission has been to interrogate the interior of Jupiter, and through that interrogation, gain a better understanding of the formation of Jupiter and eventually the quality factor of Jupiter. Nothing in that data, to the best of my knowledge, has led to a modification of our understanding of Jupiter that would lead to a younger age for any of the satellites. At Saturn, the thinking is that perhaps a Kuiper belt object came in, a rogue Kuiper belt object, perhaps analogous to Triton out at Neptune, came in and impacted a mid-sized moon or a larger moon, perhaps a sister moon to Titan, and that cataclysm created the rings and the evolution of Enceladus and Mimas and Tethys, etc. In the Jovian system, at present, there is no need to invoke some sort of cataclysmic event. And to the best of my knowledge, there is no puzzle in the Jovian subnebula as it formed billions of years ago that creates a problem with the formation of the Galilean satellites. So again, to the best of my knowledge, there's not anything that's leading to a great modification of Jupiter's Q value, but I'm not an expert specifically on that. So there could be some papers out there that are working on this.
Excellent. I don't think we have any other questions. So thanks very much, Kevin, for the talk, and everybody for attending. And I'm sure Kevin's available if there are questions after the fact to send him by email.
Yeah, my pleasure, and have a good afternoon.
All right. Thanks very much. Thanks, Kevin.
Okay, see you.